Now it is. So that whole, thank you for letting me know. I thought you were responsible for that. You're the closest person. What the heck? All right. No, it's all right. Everything I've said is useless in anyway. No, I'm kidding. So they bench test these things for certain loads, and figure out what they can handle. Well, you know that the wire, right, is going to have a certain mass to it, and then if you come in here, where does calculus come in? Well, if you come here and you look at the slope of the tangent line, right, where that comes into, where the catenary comes into the ceramic, that slope of the tangent line gives you the direction of that pull, doesn't it? I mean, that's what that insulator feels, is a force going tangent to that curve, right? I mean, the force that ceramic thing feels is not coming straight down. It's the wire pulling it straight out, and it's in the direction of that tangent line. So what you do is you can figure out what that tangent line is, what that direction is, by understanding this curve. But you need to know what the curve is, and it's a catenary. It's a hyperbolic cosine function. So I was trying to get you to see that these are useful functions. They're not just like made up just because we like making stuff up. All right. I mean, we do like making stuff up, but not that particular thing. Okay. So we have 6 hyperbolic functions, and for each one of them, we have a derivative, right? That makes sense that you would have that? All right, so here's what we have. If we have the sine hyperbolic function, and we want to take its derivative, what do you think it is? What do you hope it is? Cosine hyperbolic x, and it actually turns out that it is. And then you say cosine hyperbolic x, what are you hoping it's going to be? Negative sine hyperbolic. Well, even better, it's actually going to be sine hyperbolic x, and it's not even negative. Okay? By the way, these are all on page 186. So that's the difference between the regular trig ones and this one. Right? Regular trig, derivative cosine is negative sine. Here, it's what we wished it was back when we were learning derivative cosine. And then the rest of them are there, okay? And they're on your formula sheet also, right? Does your formula sheet have the hyperbolic trigs on them? Yes, and the derivatives of hyperbolic trigs? So they're all there, all right? So I'm not going to go through them. And guess what? Each hyperbolic trig function has an inverse hyperbolic trig function. And each of those has a derivative. So those are on page 187. Now, they only cover 3 of the inverse ones. So really, the reason why, the only thing I like to talk about in 3.6 is not like, let's get into a deep study of hyperbolic trig functions. It's more of, let's just realize that there are now these 12 new functions. Sine hyperbolic, cosine hyperbolic, tangent hyperbolic, secant hyperbolic, cosecant hyperbolic, cotangent hyperbolic, sine hyperbolic inverse, cosine hyperbolic inverse, tangent hyperbolic inverse, secant hyperbolic inverse, cosecant hyperbolic inverse, cotangent hyperbolic inverse. And every single one of them has a derivative, and it can all be referenced on some sheet, okay? So if you ever are faced with a problem where you're trying to find a derivative of one of those 12 functions, you can now reference and apply the rule. Does that make sense? Okay, I don't want to spend any more time on it because we don't have enough time to properly treat that section. We could spend a month in it just talking about hyperbolic trig functions. And I think the book, pardon? I don't remember if I've ever put a hyperbolic on there. Probably not. I mean, I do the Cal 2 and the Cal 3, and in Cal 2 and Cal 3, you never deal with hyperbolic trig functions. Never. So even that far ahead, you're not messing with these. But later on, they do come into play, like I said. Anytime you start getting e to the x, e to the negative x together, you start having to bring these back. All right, well, that leaves us nothing in Chapter 3, so we're ready to start Chapter 4. I'm not even going to give you homework out of there. We've made it to chapter 4, which is really the last major chapter that we're going to cover in this class. We will try and get into chapter 5 a little bit. I mean, my goal is to try to make it so that you have, if you're taking Cal 2, you will have some overlap, that you won't walk into Cal 2 and it's brand new from day one. Like something will look familiar to you is what I'm hoping for. But chapter 4 is all about applications. It's about what we can do with derivatives, some of the things we can do with derivatives. And the first section in this is maximum and minimum values. So this is going to be very visual, which is a good thing. Let's just talk about what we mean by maximum and minimum values, just from the perspective of a graph. If I were to draw an x and a y axis like this, and I were to draw a curve that maybe does this, and oh, there's my curve. Now I have closed this curve off, meaning I have stopped it. I want you to stop at some point A and some point over here B. So I'm not allowing you to continue to draw this function forever. We call this, restricting the domain. The maximum value of this function is the highest point that it reaches. Does that make sense to you? That would be something like this point right here. That point comes from somewhere, right? Some x value. Now, I don't know what it is, but then there's some corresponding y value up here, right? So it's a point. The x value is the x-coordinate of that point. The y value would actually tell me how high it is, wouldn't it? The y value would be the height. So that would be considered the absolute maximum of this curve. Absolute maximum. Now, what about minimum? It would be the lowest point on the curve, right? So maybe initially you would be looking and saying, hey, that looks like the lowest point on the curve. Maybe that's what your eye would have been drawn to, but it's not, right? Because this endpoint right here is lower than that, isn't it? In fact, there's a bunch of points over here that are lower than it. But the one on the far left is going to be your lowest point. So this right here would be considered our absolute min. Now, along with this idea of absolute maximum minimum, if we define a function on a closed interval like this from a to b, we should only have one highest and one lowest value. Okay, we can't say that the highest it ever is 2 and 3. Like it's got to be one or the other, right? So it's either, in that case it would be 3, right? So you can have one absolute max, one absolute min, that's it. But then you can start talking about what are called local maximums and minimums, which means you don't have to spread your eyes across the whole graph. You just have to look in that local little area and say it's the highest or lowest point. So how about this? How about this point back here that we had said is not the absolute minimum? Could I consider that to be a local minimum? Yes, so the idea, though, that you have to kind of toil with here and struggle with is the fact that what do you mean by local? What is local? Local usually means like, close to you, I guess, right? Your local post office. Doesn't mean the one in Washington, D.C., right? I mean, local is... So normally we mean local being close, close to. So we're saying if you look around just this little locality, this little area here, this little region, that is the lowest point on the graph. Once you go outside of that locality, it's not the lowest anymore. But do you remember we had the same problem with limits? We were talking about what does it mean to get close? I think I gave an analogy of something like, am I close to you? I think it was you, right? I said, am I close to you right now? Am I close to SeaWorld? Am I close to the sun? What do we mean by close? Same thing here. What do we mean by local? But we aren't gonna mess with that. We're just, from the graph, I think we can all agree that if you lived around in this area, you'd say that that point's the lowest. Now, where would I have another local, or how about a local maximum? Can someone point out a local maximum? What's that? This pointy thing, we call that a cusp, right? Right there at that point up there, that would be a local max. Right? Do we have another local max? Yep. Over here? Do we have any other local minimums? Yeah, over here. Local min. So all I'm trying to get you to see is where these things are happening, right? We have an absolute minimum at this endpoint. We have an absolute maximum up there. Oh yeah, is this a local maximum? Yes, it's a local maximum, but it turns out it's actually the absolute maximum also. So if you wanted to, you could say that that's a local max. Pardon me? That's a good question. That's what I was about to address next was, is this going to be a local minimum? Is it the lowest point in its little region? Well, if we say there's nothing allowed to be over here, right? You can't come over here, then you would say that over here, locally, it is the smallest, right? So yes, you could call that a local min, and you could also call this a local min over here at this endpoint. It's not wrong to do that. Okay. So I want you to try and take a look at, I'm going to highlight our local max and mins that are not on the endpoints, okay? I want you to think as a calculus student about the derivative. I want you to tell me what's happening at all those yellow points. Tell me about the derivative. How about that first yellow point, top left? What's the derivative there? 0. What's the derivative here? What's the derivative here? Doesn't exist. What's the derivative at the next one? 0, and the next one? 0. So if I come in here and draw derivatives at slopes of tangent lines, it's 0, it's 0. Here, dne, right? Derivative doesn't exist. Here, 0. Here, what? 0. That starts to make me believe that perhaps I can find the maximums and minimums, local maximums and minimums of any function by just asking myself where the derivative is 0 and where the derivative doesn't exist. Maybe that's going to be the answer to how to find the highest and lowest points on any graph. Does that make sense to you? So why don't I draw something else and kind of spoil your little mental party you're having there? How about if I draw this? Here's my curve. I put arrows on there to symbolize that this is going to go forever. Does this graph have a local max, a local min, or absolute max or absolute min? No. Just goes forever in each direction. Looks like it's diving down to the left forever, up to the right forever. Doesn't look like locally there's any highest or lowest points, right? No king of the hill, no bottom of the valley type thing. No cusps. But take a look at this. What's the slope of the tangent line right there? What does it look like? Looks like it's, positive, right? And then it looks like it becomes what? 0, and then goes back like that, right? So the slope of the tangent line here is 0. And then what about this point right here? What's the slope of the tangent line here? It doesn't exist because it's straight up and down, right? So we have it does not exist. We have that this is what? The derivative is 0 here. But neither one of them is a local min or a local max, right? So we were all like patting ourselves on the back going, ha ha, we found a way of figuring out the highest and lowest points on graphs by just looking at the derivative and saying when it's equal to 0, when it's not. That make sense? And then we threw this in here and said, too bad, that's not necessarily going to work. Right? Now it's okay, because we're going to have a way around that. All right, we're going to be able to still do this. We just have to be careful. We have to be very, very careful when we do this, that we investigate this graph a little bit more before we conclude that we're at a local max or a local min. Understand, at least geometrically, what's going on? Geometrically, do you have any idea of what? Was that, yeah. Our goal, this section is called maximum minimum values. Our goal is to try and find maximum minimum values of a function, the highest and lowest points, basically. What I'm trying to get you to see is that maybe perhaps the slope of the tangent line or the derivative is going to lead us to those points. Is that all right? But we have to be careful because sometimes it can happen that the derivative tells us something that actually doesn't lead us to a max or min. Is that all right? Okay. So there are two things that we're going to approach in this chapter. Trying to find the maximum and minimum values of a function when we do not cut it off and let it go in both directions forever, something like this, and we don't cut it off. Or we're going to try and find the maximum and minimum values of a function where we do cut it off. All right? If we do not cut it off, this is called the open interval method. And then this one is called the closed interval method. And as we're about to see, if somebody gives you a function and they cut your interval off, so they give you a closed interval, and they say, just look here, it's going to be much easier to find the highest and lowest values of that function than it will be for us to do it with the open interval where they say, here's a function, but they don't cut your domain. They say, just look everywhere and find me the highest and lowest values. So we start with this. We will get to that, all right? All right, so we're focusing on this in this section. Before I can do it, though, I have to define some stuff. So this is a definition for you. A critical number. A critical number of a function f is a number C such that one, f prime of C equals 0, 2, or I should say, or 2, f prime of C it does not exist. That is the definition of a critical number. Any number see that when you try and plug it into your derivative is going to give you back 0, or your derivative is going to not exist. Now, they're called critical numbers because they are critical in aiding us in determining these max and min values. So back to my picture. This one. No, I went too far. This one. Any number where the derivative would have been 0, doesn't exist, would have been a critical number. So would you agree with me that this x value that I just circled here is a critical number? It is some value, I don't know what it is, but it's something that when I plug it into the function and I take the derivative, I got 0. Yes? So I'll call that x1. How about this right here? x2. Would that one be a critical number? Yes. How about this one right here that gave me does not exist? Yes. That would have also been a critical number. And then here would have had another one. And here would have had another one, right? So I would have had, what, 5 critical numbers here? 5 places? Any questions on the geometry of that, or how I'm relating the critical number to that picture? So that's the definition of a critical number. And now we have a pretty major result from this. And it says this. If f has a max or min value at C, then C must be a critical number. If f has a max or min value at C, then it must be a critical number. If it has a max or min at C, it must be a critical number. We have to be extremely careful not to read this the wrong way. So maybe a quick little lesson in logic and implications. There's some key words here. If this is true, right, then this is my conclusion, right? If the blue is true, then the green is true, right? That's what that's saying. If your function does have a maximum or your function does have a minimum, then I promise you that that place that it's happening must be a critical number. That means the derivative must be 0 or the derivative must be undefined there, right? So let me write something below this and see if you can see what I mean by the logic is important here. If you are in this class, then you go to Northwest Vista College, right? You agree with that? If you're in this class, well, then you go to Northwest Vista. Everyone agrees with that, right? We're not going to get an argument about this. And there might be someone here just for fun, right? Free what? Can you read these the other way around is what I'm getting at. Can you change the order and it still be true? No. If you go to Northwest Vista College, then you are in this class? Does not work that way, right? The other way around does. If you're in this class, you must go to Northwest Vista College. The same thing is true for this statement, and this happens all throughout mathematics. If you have a statement, the way it's written is not just like, If that, then this. It has to be very careful about the way you write it. You have to. Have y'all ever seen in a mathematical statement, if and only if? Have y'all ever seen that in a math? And have you ever understood what it means? It doesn't mean like, no, this time really, if and only, like we're real serious about this one, so we use if and only if. What if and only if means is that the implication goes both directions. It means that whatever they're saying is true, if and only if the other one is true, means that you can read it backwards both ways, and it's still true. This does not work that way. This is a forward implication only. If you're in this class, then you go to Northwest Vista. If you have a maximum, then it must be a place where the derivative is 0 or undefined. If your derivative is undefined or 0, that does not mean you have a maximum. I just gave you the example. Here's a picture of a graph where I have a value c, right? Where the derivative there is what? 0. I have a critical number, right? I have a place c where the derivative is 0. Does that mean I'm at a maximum? No. I have another place over here, c prime, where I go here, slope of tangent line, undefined, right? So this is a critical number. It's a place where the derivative is undefined. Does not exist. Does that mean I'm at a local max or minimum? No. So I'm trying to illustrate the importance of the logic here. Just because you're at a critical number, that does not mean that you have you have found the place. But if you have found the place, I guarantee that the derivative was 0 or undefined. So let me try. I'm going to try, if I can possibly do it, to draw something that has a max and a min without making the derivative 0 or undefined. So how can I do it? Let me see. Try and put a maximum up here. So it means I'm going to have to come back down, right, at some point? Like there's my max. And by doing that, I have a max, right? But there is no way to avoid the fact that at the maximum point, the derivative was 0. I could not avoid it. If I draw it to have a minimum value, maybe I try and get clever and I do a cusp, right? Now I've created a minimum. My derivative is not 0 there, but my derivative is what? Undefined. Derivative does not exist. So the theorem that I just gave you reads this way. If you have a maximum or a minimum value at a point, it's guaranteed that the derivative there is 0 or undefined. Y'all okay with that? If x equals 2, sorry, I'm going off on something here. Then x squared equals 4. Do you agree with that? That true statement? If x is equal to 2, then x squared is equal to 4. Okay? If x is less than 0, then x squared is 4. Do you agree with that? I've somehow slowly gone off on a tangent right now. I hope you all realize I'm getting into logic right now. We all agreed with the first statement. If x was 2, x squared was 4. We're all happy with that? How about this next one? Okay, so in order for me to say that this is true, it has to always hold. Which means if you come up with one example where it doesn't hold, it's not true, right? So what did you say, 3 or negative 3? It'd have to be negative though, right? So if my number is less than 0, it has to, when you square it as 4, that makes no sense. If I just so I say, suppose, this is the way we write suppose x equals negative 3. Then x is definitely less than 0, and x squared equals 9, which is definitely not 4, which means I've proven you wrong. So that statement is not true, right? Okay, let me try one more. If x squared is less than 0, then Robert is All right, I'll do that. I was going to go a little worse than that, but I'll do that. And also I should say here, x is a real number, which means you're not allowed to use imaginary numbers here. So in mathematics, in our logic, is this true? Why do you think it's not true? Right, because I'm not bald. Because if it were true, I'd be bald. Oh, my hair's all going to fall out. If I square a number, it should always be positive, right? As long as it's a real number. If they're imaginary numbers, we know like I squared is -1, but that's a long time ago. All right, we won't even talk about that. So if it's a real number, x squared less than 0. This, in logic, in our logic system, the way it is, all right, the way we all agree to do logic, this statement is true. All right? It's what we call vacuously true. If your assumption is false, your conclusion doesn't matter. My assumption is never true. So my assumption is false. So my conclusion is always true. False assumptions lead to true conclusions. It's weird, but that's where our logic is. Has anyone taken a logic course or anything? I would always recommend anyone who really wants to do math, like seriously, not like engineering, but like if you are interested in math, take a logic course because it'll really help you prepare for how we prove things are true in math. You have to understand the logic of things. Here's another logic problem for you. This statement right here, tell me if this is true or false. This is a statement. All the pink elephants in this room have wings. All the pink elephants in this room have wings. Exactly. Yeah, I mean that's a true statement until someone can prove it wrong. Right? So how would you prove to me that all the pink elephants in this room don't? Well, I said all the pink elephants in this room have wings. In order to prove that wrong, you would have to produce a pink elephant in this room that does not have wings. You see what I'm saying? It's vacuously true. There aren't pink elephants with wings in here. But to actually negate it or to actually prove it wrong, you must do something. You must come up with a contradiction, which you won't be able to do. So it's vacuously true. Does that make sense? That's the way our logic system works. We have in our logic system two possibilities in a statement, true or false. There is no middle option. It's called actually the law of the excluded middle. When you have a statement, it's one or the other. You can't both be true and false simultaneously. Last one, I promise. Ready? If Robert cuts the hair of all people in San Antonio who don't cut their own hair, who cuts Robert's hair? So if Robert cuts the hair of everybody in San Antonio who doesn't cut their own hair, who cuts my hair? Okay, so let's try and think about it. Can I cut my own hair? Okay, so Robert cuts the hair of everybody who doesn't cut their own hair. So I can't cut my own hair because then I'd be cutting the hair of someone who doesn't cut their own hair. So I'd be cutting my own hair. It can't be me, right? Okay, so if somebody cuts my hair, right, then I'm not cutting my hair, right? But Robert cuts the hair of everybody who doesn't cut their own hair. So yes, in San Antonio. So it would have to be someone from Austin or something. But the idea, again, it's one of these weird circular logic things where you can't find or produce a correct answer. And that's what logic is all about. It's in mathematics, when we're trying to prove things, when you have a theorem presented to you in math, the order, everything is important. The language of everything is important. We don't leave out a single word or detail. It's all there for a reason, and it's all based on logic. You know, can I say that there is a number that when I square it, I get 9? Yes. There does exist a number that when I square it, I get 9. Can I say for every number, when I square it, I get 9? No. So there's this thing of like, okay, showing the existence of one example versus it applying for everything. All right, I'm way off topic. I apologize. Where was I? Here we go. So if we have a max or min value, then we know it must be at a critical number. Now we get to, if you're going to take anything away from this, here's the note right here. It's the method of how to find the maximum minimum values of a function when you close it out on an interval. All right, so here it is. The closed interval method. This is what we use to find, this finds actually the absolute max and min. All right? This method I'm about to give you will give you the absolute maximum and minimum value of a function on a closed interval. So the first thing we need is to make sure that f is continuous. All right? F must be continuous on a closed interval AB. When I say closed interval, I mean it's between 2 points. You include the endpoints. If that interval is not including one of the endpoints, you throw this out the window. You can't use it. All right? Has to be a closed interval. All right, so first thing, f is continuous on a closed interval. That's what you check for. Second thing you'll do is find the critical numbers of f. Now, what does that really mean? Find where the derivative is 0, right? Find where the derivative does not exist. So I'm going to kind of put that in here in blue. That means you're going to find where the derivative is equal to 0, and you're going to also find where the derivative does not exist, where it's undefined. The third and last step, take critical numbers that basically means your answers, your answer or answers, you might get more than one, from part 2. So you take those critical numbers that you just got in part 2, take your endpoints. What do I mean endpoints? A and B, so I'm referring to A and B. And what you're going to do with those critical numbers and those endpoints is you're going to just plug them into the original function. You're going to evaluate your original function at the endpoints and at the critical numbers. So take the critical numbers, take your endpoints, and plug into into original function. F. Now let's try, I'm going to give you the conclusion here in a second, but let's just try and think about why it is we're doing this. Imagine this picture below. I'll do it on a new page. I'm not done here, so leave yourself a little bit of room below this, maybe for like 1 or 2 more lines. Here's what I'm doing. I have a function that's defined on a closed interval, which means I could take that value A and I could plug it into the function, right? And get a value? Yes? And then I have some other endpoint B, which is they're giving me in the problem, right? Because they're closing off my interval. I could plug that into the function and I could figure out where that is, right? Yes? Okay. Now, I go in, I find the critical numbers. The critical numbers, maybe I have one right here. I'll call it C1. And maybe at C1, I can't really tell you anything other than the fact that the derivative is 0. And then I go and I find some other critical number and I tell you that there, maybe the derivative is 0 again. And then maybe at C3, I can tell you that the derivative does not exist. You with me? Then I don't know, okay? Also, let me put C3 in here. I have a dot. I actually don't really know what the picture looks like, right? I don't know what it looks like. But I know that my max and min values are going to have to occur at one of those points, right? If it has a max or min, it has to happen at a critical number. Or it could happen at the endpoints. With the very first example, remember that left endpoint was the lowest point? So it's either going to happen at my critical numbers or at my endpoints. That's where it would occur. And because there are a finite number of points, all I really need to do is measure the height of each of these points, don't I? And compare them. The highest point I get is my max. The lowest point I get is my min. So instead of going and trying to figure out what's happening, all I do is figure out what the critical numbers are. I take the endpoints. I plug them all into the original function. The largest value I get is my max. The smallest value I get is my min. And I'm done. Does that make sense? The largest is max, absolute max. Smallest is the absolute min. We're going to do an example now. Find absolute max and min values of the function f of x equals x cubed minus 3x squared plus 1 on the interval -1/2 to 4. It's like exceptionally dark in here. I'm sorry, did I wake you up? No? It's like a little too dark, a little too gloomy outside for us to have those many lights turned off. Okay. All that yapping earlier about everything, we finally have gotten to like, okay, what are you going to be tested on? What are you going to have to do? Here it is. So I have a polynomial function, right? Polynomial? All polynomial functions are continuous everywhere. Remember, continuity meant you can draw it without picking up your pencil, basically? This is a continuous function everywhere. I have a continuous function on a closed interval. which means, and I'm trying to find the max min, so I'm going to use the closed interval method here. If this was not here, you could not do this, and you have to wait till like later on in the chapter, 4.3, before we can do that, right? But for now, we can use the closed interval method. So using closed interval method to find these, the first thing I check that f is continuous. Yes or no? Yes? Do I have a closed interval AB? Yes. Okay, you're allowed to use this then. Next thing I'm going to do is I'm going to find the critical numbers. The first part of finding the critical numbers was to try and find where the derivative was 0, which means you have to take the derivative, right? So take the derivative of this function. What is the derivative of that function? 3x squared minus 6x. And I finally get to do something with this derivative. I get to set it equal to 0. And now I get to solve equations, right? All that time in college algebra solving equations, we finally get to use it. So this is a quadratic equation. So normally when you solve a quadratic equation, you get everything to one side, but we're already there. And then I always look for GCF first, which I have, right? What's my GCF? 3x. I pull that 3x out. I'm left with what? X minus 2. And this gives me two solutions, doesn't it? 0 and 0 and 2. These are my potential critical numbers. I do have to check one more thing, and I didn't mention this earlier. You have to verify that these actually live in the interval that you're looking in. So let's go back up here. -1/2 to 4. If I were, you don't have to draw a number line, but if I were to do it, here's -1/2, here's 4. Does 0 live in this interval? Yes. Does 2 live in this interval? Yes, so I will consider them both. If this had turned out to be like x is 0 and x is 5, I would just cross out the 5 because it's not in my interval, so I'm not going to pay attention to it. It's referring to something that's not where I'm looking. Okay? Very important that you don't forget that, because it'll happen where you get a critical number that doesn't live in your interval. Okay, so that's step 2. I found that. Oh, wait, I'm not done with step 2. I also need to figure out what with step 2. Where the derivative is undefined or does not exist. But wait a minute, what was the derivative again? 3x squared minus 6x? That was my derivative, right? Is this ever undefined? Is there a number you can plug into that to mess it up? No, it's a polynomial, right? It's a well-defined, nice-behaved function. So there's nowhere that you're going to get division by 0, square root of negative number, anything crazy like that. So because of that, this does not happen. You do not have to worry about anything making your derivative not exist. So the only two critical numbers you have are 0 and 2. So what's the third step of the closed interval method? Plug those numbers and the endpoints into the original function. So let me first make a list of my critical numbers and my endpoints. And it doesn't matter what order we go in. Here are my critical numbers. Here are my endpoints, right? I have 4 numbers, the 2 critical numbers and the 2 endpoints. And now I get to plug all of those in to the original function. So my original function is on a different page, but it was x cubed minus 3x squared plus 1. So if I plug 0 in here, that's the easy one, right? 0, I get 1. What if I plug in 2? 8, take away 12, that's negative 4 plus 1, negative 3. What if I plug in negative 1/2? Well, that'll be negative 1/8 minus 3 times positive 1/4 plus 1. So I cubed negative 1/2 and it gave me negative 1/8. I squared negative 1/2 and I got positive 1/4. I add 1, add 1. Now I need to clean this all up. Let's see here. Negative 1/8. Take away 3/4, which is 6/8. And then add 1, which is 8/8. So I'm just rewriting the negative 1/8. I'm going to subtract this, which is this, and then 1 is, I'm just getting common denominators all the way across. And then put all that together, you get 1/8. And then plug in 4. 4 cubed. What's that? For which one? This one? Did you square? Did you cube 1/2? Oh, you did on your calculator? There's probably some parenthesis problems there. When you, yeah, I'll have to check, but I'm pretty sure this is good. Rewrite this right here. This becomes negative 3/4. Multiply top and bottom by 2 to give you negative 6/8. Just to get a common denominator, put them all together. What about 4? Look, this is like college algebra stuff. Plugging numbers into functions is not something we should get hung up on. Now, you may have to take your time through it, right? But this is very mechanical. So I would expect that you could get this eventually given enough time. But not like 30 minutes, right? I mean, this shouldn't be like 30 minutes on the test just to plug in 4 numbers. It should go pretty quick. 4 goes in here. What's 4 cubed? 64. 64 minus 48 plus 1, 17. So what are we doing all this for? Try and find the maximum minimum, right? So what is the maximum value that this function takes on that interval? 17. The minimum? Negative 3. And where do they occur? See, what I like to do is I like to box these, because this not only tells me what the maximum value is, it actually tells me where it happened, right? If I plug in 4 for x, it spits out 17. That was at the end point, wasn't it? When I plug in 2, I get negative 3. 2 was one of my critical numbers. So that was somewhere inside the interval that I hit my lowest point. Now, I could always verify this with the graph. Is everybody okay today? I'm looking out there, and it seems like a lot of you are just like dazed and confused today. Is it just the weather? It's the weather? Okay. What? Do I want to know what you said? Okay, so here we go. Here's the graph, okay? Here's the graph. But this, I have not restricted the interval. All right, there it is. That's the graph of that function. Now I will restrict the interval. I'm going to come back in here. It was between negative 1/2 and 4. Now I've cut it. Yeah, it's going to be way up there. There. Okay? Between negative 1/2 and 4. The highest value we had was 17. It happened way up there at the end point. And the lowest we had was -3, which was here. It happened at 2. You see that? We could do all that without even looking at the graph. And that's the point of all of this, is to find the highest and lowest values of functions without needing to look at the graph. Yeah, I mean, notice how nice this function was? Notice how when you took the derivative, it was quadratic and it factored. Now just imagine that it's going to get pretty ugly because the derivatives are going to be ugly. And I had told you a while back, be prepared that at some point these derivatives that we're saying is the raw derivative would have to be set equal to 0. Remember me saying that? Today is the day. All right? The day has arrived where you have to set these equal to 0 now. But we have to baby step into them. Huh? Yeah. It's all fair game at this point. Yeah. Mhm. Like a review day. The what? For chapter, the previous chapter? When's our next test? 26th. You, is it the day before Thanksgiving? Ooh, wow. We might have to move that to Monday. Monday before. Wouldn't you all rather have it the Monday before Thanksgiving? How many of you are okay with doing it the Wednesday before Thanksgiving? Because I know some people travel, so how many people are definitely not okay with doing it Wednesday before Thanksgiving? Oh, so you're okay with that too? Okay. I didn't realize when I made it that, I mean, normally on the Wednesday before Thanksgiving we can't get people here. Like, people don't show up. We have to be here no matter what. But look, let's can we address that like later, not right this minute? I mean, I can't commit to any time right now. The reason why, say it this way. That was funny. All right. So you like to try something a little more difficult, maybe? How about this? This will be probably our last example. Find the max and min values of f of x equals, man, okay, here we go. X square root 4 minus x squared negative 1 to 2. All right, do we have something that's eligible for the closed interval method? Well, we're being asked for maximum value, right? We're given a closed interval. We're given a function. I think that function is continuous. We always have to be careful with square roots, don't we? Because it is possible that you could get a negative number under here. So you would maybe have to investigate this a little bit. You'd have to ask yourself, when is the when is the radicand, greater than or equal to 0? Because we got to make sure this is greater than or equal to 0 in here, right? So just move the x squared over. And so we're saying whenever x squared is less than 4. So let's just look at this interval here. If I plug in 2, am I good? Okay, if I plug in -1, am I good? If I plug in something between them, let's say 0, am I good? Yes? Looks like everything in that interval is going to be okay. So my function looks like it's well defined. It's continuous on the interval in question. So we should be able to use a closed interval method. So closed interval method. The first step was to verify that f was continuous. Yes, on the closed interval. And maybe you don't see the value of this right now, but later on, this will be where we turn off, when we're going and we're doing a problem, this will be where we turn off in one direction or the other. We're going to say, okay, we're either going to do closed interval method or we're going to go do open interval method. So doing this check is real important. Second thing, you need to find the critical numbers, right? Derivative, set it equal to 0. Now, the last derivative was pretty clean, wasn't it? This derivative, not so clean. It's going to require what to do this derivative? Some product rule and some chain rule. Your two favorite things. Well, hold on. I left out the quotient rule. I apologize. Maybe another example. All right, so let's work this derivative out. The derivative is product rule. The derivative of the first one, here's my product right in here. The derivative of the first one, which is 1, times the 4 minus x squared, right? Plus, now, the derivative of the second one, which is a square root. So I've been trying since the beginning of class to get everyone on board with the idea that the derivative of the square root of something is 1 over 2 times the square root of that something. And so that's what I'm going to stick with. And especially now, I think you're going to see that it really helps you if you write it this way with where we're going with it, right? Because we're going to set this sucker equal to 0 in a little while. Now that's just the derivative of the square root of something. I still need what here? The derivative of the inside. What's the derivative of the inside? Negative 2x. And I still need to finish off the product rule, so times x. And we used to, at this point, be like, like a sigh of relief that we were done, right? Well, now we have a lot more to do, right? Because I need to set this thing, which looks pretty bad, equal to 0. So setting the derivative equal to 0 means I need to set, let's see, I'm getting rid of that 1. I'm just going to rewrite. I'm just rewriting right now. So what did I do there? Crossed out those 2's, right? Canceled the 2's. I had a negative there, which made it a negative x squared. But I went ahead and put that negative in between them instead, right? On the first one, the 1 times that root's just that root. And now I have the pleasure of solving this equation. Any ideas? Common denominator. You could do a common denominator. What else? Okay, so find an LCD basically and multiply both sides of the equation by the LCD. Both of those are completely valid ways of solving this. It's really going to be up to you. They're both going to kind of result in the same thing. But because we do have an equation, and because it is equal to 0, I do like the idea of multiplying both sides by something. Because you know on the right side it should go away, shouldn't it? Okay. But let's all remember right now, I'm going to highlight this. This is our derivative, right? Before we've done anything. That's our derivative. Yeah? Okay, so I'll come back to this in a little while. and say and point something out on this. But for right now, let's multiply both sides of this by the LCD. What's the LCD? Least common denominator is just this right here, right? So multiply this root 4 minus x squared here, here, and here. What happens when I multiply root 4 minus x squared times the first one? It goes away. No, the root goes away, right? And you're just left with 4 minus x squared. And then what happens when I multiply this fraction on top by root 4 minus x squared? They cancel out and you're left with just x squared, and it was subtracted, right? So minus x squared. And then equals, now the other side, you multiplied that radical times 0 is your 0. So from this step to this step, I multiply both sides by this. And believe it or not, this is just a quadratic equation. Combine negative x squared is negative 2x squared. I'm going to go ahead and choose to move the negative 2x squared to the right side. I'm going to divide by 2. I'm going to take the square root. And whenever you take the square root on both sides of an equation, you always have to look at plus or minus. X could be positive square root of 2 or negative square root of 2. Let's go look at the interval. Let's go look at the interval. What was our interval? Negative 1 to positive 2. The square root of 2 as a decimal is like 1.414 something. So this is like positive 1.414 and negative 1.414. So we can throw out the negative. So for this, I'll just say x equals positive root 2, x equals negative root 2. But this one is outside the interval, so I'm just looking at this. Are we done with step 2? No. What else do I have to do? Figure out where the derivative is undefined, right? Where the derivative does not exist. So let me go back here. I'm trying to do it all on one page, but I guess I won't be able to. I want to know where the derivative doesn't exist or is undefined. So take a look. Now I go back to that highlighted thing. Can you tell me somewhere where it doesn't exist? X is 2, right? Look, if x is 2, won't you get 0 here? Square root of 0 would be 0. You get division by 0, which would be a problem. Other than that, it should be okay because we already know the square root function was fine, wasn't it? Look up here. We said that this was fine on this interval. And in fact, 2 could be plugged in here because 4 minus 4 would be 0, and that's okay. But when we took the derivative, the square root appeared in the denominator now, and that would give us division by 0. Do you see that? Y'all follow me? Okay, so for part 2, at x equals 2, we have a critical number. It just so happens, though, x equals 2 is also what? One of your endpoints. So your third step now is to plug in your critical numbers and your endpoints into the original function. So what are my critical numbers that I'm going to plug in? Root 2 and 2, what are my endpoints? Negative 1 and 2, but I'm not going to do 2 twice, right? I don't need to plug it in once, that's all you need. And we are there to figure this out. In an effort to save some time, let me just do this real quick. This is going to be root 2 times the square root of 4 minus 2 which is root 2 times root 2, which is just 2. When I plug in 2, I get 2 times the square root of 4 minus 2 squared, which is just going to be 4 times 0, which is 0. And when I plug in negative 1, I get negative 1 square root 4 minus negative 1 squared. So negative 1. Why did I put 4 there? It should be 2 times 0. All right, we're just plugging numbers into the original function here, right? The original function was x square root of 4 minus x squared. I'm getting 2, 0, and root 3 as my answers. Negative root 3, yes. Negative root 3. So we have a maximum, right, of 2 and a minimum of negative root 3. Yeah, it wasn't in our interval. If you go back to our interval between negative 1 and 2, here's negative 1, here's 2 on our number line, right? Negative square root of 2 is approximately negative 1.414, which would be somewhere over here, right? Instead of, okay, so that's why we threw that one out. All right, so here's what I think you should take a look at for your homework. Page 209. I think you should do 23 through 39 odd. But here's the thing you have to pay attention to. 23 through 35 odds. Right here, these, just find critical numbers. Here's what I'm getting at. Finding the critical numbers means you are taking the derivative and you are setting it equal to 0 and finding out where it's undefined. You do not have to go back and plug it into the function and all that stuff. It's practicing, those problems right there that are circled, are practicing taking the derivative and setting it to 0. Taking the derivative, setting it to 0. And then 37 and 39 is the full-blown deal. That's where you go through, you compare, you take the endpoints, you plug them in, you do the comparison, all right? So do those first sets of problems there, and that'll get us at least warmed up with differentiation and solving these. Have a good weekend. When were you hoping to have a study thing for Chapter 3?